Today we're going to talk about the difference between linear and exponential functions. So the first thing I want you to do is I want you to take your foldable, fold it halfway in, and this is going to show us what these different pieces look like side by side. Okay, so we're going to start with the ones we know, which is linear. Okay, keep in mind that linear, when we look at our equation for linear, it is y equals mx plus or minus b, where again, m is our slope, our rate of change, our change in y over our change in x. And b is going to be, again, just as a review, y-intercept, the value of y when x is 0. This is all stuff you've been doing for multiple years. When we look at a table that is linear, right, here is our b value. And then we have plus 4 for our change in y, and plus 1, this is our change in x. So we could say our slope is 4 over 1, our b is 3. When we were talking about sequences this last go around though, we didn't use the word slope, we used common difference. Okay, so that would keep in mind that those can be interchanged. The only difference is if you are starting with 0 versus 1. Okay, if we looked at a real world situation, your savings account starts with $300. Every Friday you deposit $50 into your account. So we could make a table for this where we are starting, we have $50 into your account. So this would be, you have money, and then you have whatever Friday it is, right? So you're starting with 300. After the first Friday, you have 350 and 400 and so on. So you can see, in fact, that slope common difference right here. Here's your b value. You can say y equals 300 plus 50x. If we were to write this as a sequence, you would write a sub n is equal, now we're starting at 350 plus 50 times n minus 1. Same difference. Okay, if we simplified this, we would get the same thing. When we create a graph of a linear equation, it is in fact going to be straight. If I was to make a table for this and I said -1, 0, and 1, we could plug that in. -3 plus 2. If you wanted to see your process right here is -1. 3 times 0 plus 2 is 2. 3 times 1 plus 2 is 5. So when we create this graph, -1, -1, 0, 2, which is our y-intercept, 1, 5. You could even start like we did before with the y-intercept and count rise over run. Okay, and you can see that our line is straight for linear. So that's a nice little recap for that. Let's talk about, on this other side, exponential. Notice that this equation does not look like our linear equation. This has times instead of plus. We have an exponent, which makes sense since it's called exponential. So our format, instead of y equals mx plus b, is y equals a times b to the x power, where a is our initial amount, kind of like our y-intercept. Actually, it is the y-intercept. And B, this is going to be that common ratio that we talked about with our geometric sequence. Okay, that's going to be our increase, decrease. So when we look at this table, we can see, in fact, that it is not adding the same amount each time. Well, 3 times 4 is 12. 12 times 4 is 48. 48 times 4 is 192 for every one. Okay, if you're struggling to figure out what that common ratio is, take your previous term, so the one ahead, so we can say 12 over 3 is 4, 48 over 12 is 4 to get that common ratio. Okay? If we were to look at a word problem, your savings account starts with $10 and it doubles every month. So we have month here, we have money. If we're starting with $10 and it's going to double, that means that common ratio is times 2. So 20 times 2, 40 times 2, 80. Okay? And the equation here would be our initial amount times our common ratio to the x power. When we were writing this as a geometric sequence, then we would start with 20, because that's our first term, times 2 to the n minus 1. Keep in mind that these are exactly the same. If you were to go to your calculator and you were to create a graph of both of these, 10 times 2, and to get that exponent, if you don't remember, right here you have this little caret below the equals to the x power. So as you can see, this is not going to be a straight line graph. We can also graph this one, 20 times 2, again with that little caret, but now I'm going to use x minus 1. It does overlap, it is the same line, but I want you to see that they do simplify to be the same thing. If we're going to graph 3x times 2 to the x, then we need to keep in mind our exponent rules. Okay, so I'm just going to start, I'm not going to do any negatives on this one. I'll do 0, 1, and 2. And you already saw on the calculator that it is, in fact, going to be curved. And you could even use your calculator if you wanted, if you're not sure about your exponents. All right, we will learn some exponent rules a little later on. So I can say 3 times 2 to the 0 power, I get 3. We'll learn that anything to the 0 power is in fact 1 a little later on. We can say 3 times 2 to the first power is 6. 3 times 2 to the second power is 12. Because if you don't remember your order of operations, that's going to be a little bit tricky. Sorry, my lights just went out. So there you can see on my calculator. If we're going to graph this, 0, 3, 1, 6, and then this is where it jumps up 2, here's 6, 7, 8, 9, 10, 11, 12. And you can see that this is in fact going to be curved. It's going to get really, really close to this x-axis. This is what we call that asymptote. We talked about that a while back. But this one is going to be a curved line. All right. So we're going to talk some more about this in class today.